So I'm going to talk about a paper that was posted on arXiv very recently called Threshold Functions for Incidence Properties in Finite Vector Spaces. And this is joint work with Jeong Han Kim, Thang Pham, and Semin Yoo. So the threshold functions I'm talking about are like Erd H threshold functions. They were studying random graphs. And notice a general phenomenon that you take an Erd H random graph and ask about some property. For example, does it contain a triangle or is it connected? And there will be a very specific probability under which the probability that it has a property is 0 and above which it has the probability that it has the property is 1. And I'll make that a little more formal. This talk is going to be really organized into two parts. First, I'll talk about just for general set families, introduce some notation, definitions, and the tools that we use from probability. And then the second part of the talk, I'll talk about our main results for threshold functions for subsets of finite vector spaces. So first, let me introduce a notation and definition for what a threshold function is. Let's take F is a family of subsets of some underlying finite set U. And here, actually, it's important to think about, this is not defined necessarily just for a single set U, but for some infinite family of underlying sets of increasing size. So, for example, you could think about if the property that you're interested in, if you're interested in, say, random graphs, then the set U is going to be the set of edges of a complete graph. And if you're interested in the property, is it connected, then the set F would be the minimal complete connected graph. So, for example, spanning trees. And then the property that your graph is going to be connected if and only if it contains some element of F. So F is are the minimal elements of an upward closed property. So E will be a random subset of U. Each element taken with probability theta. So let me say X and E with probability theta. And independently. So an element is in E with probability theta independently of all other elements. And then gamma is going to be the event that there exists some set F or some set S in F that's also contained in the set E. And so we say that T is a threshold function for F if two things hold. First of all, if the probability is smaller than T, we should not have the property. So one, probability of gamma is little o of 1. And here the asymptotic parameter, for example, could be the size of U. If theta is little o of T. And 2, the probability of gamma is 1. 1 minus little o of 1 if the theta is much larger than T. And I'll also use a finer property, or which is a sharp threshold. And so we say that F is or T is a sharp threshold. If For all epsilon greater than 0, we have, again, the same two alternatives, but now the probability of gamma is 0 in the limit if the probability theta is bounded above by 1 minus epsilon times t 2 exact. 1 minus little of 1. The probability theta is at least 1 plus epsilon. So these are two notions of what it means for a function to be a threshold. And it was shown by Bolabosh and Thomason in the 1980s, I think, that all properties of this nature have a threshold. So when you're looking at a property defined on some family of sets, the only things to answer are, first of all, what is the threshold, and second of all, what does the property look like at the, or what does the, how does the probability move from 0 to 1 at the threshold probability? For example, it's not the case that every property has a sharp threshold, so this gives some additional information. So now let me say what the tools that we use from probability are. We have, I'm going to assume for now, it's not the case in all the applications, but for the time being, I'm going to assume that we're dealing with an L uniform family F. So say F is L uniform. Now there's a simple observation, is that there always exists a threshold function t that's at least the cardinality of f to the minus 1 over L. And for the proof of this, well, the probability gamma here is the event that your random subset E contains some element of F. If I define, let me define X to be the number of elements of F. And by Markov's inequality, this is at most the expected number of expected number of elements of F that are contained in E. And this we can calculate. This we can calculate quite easily. We know how large each element of F is, so the probability that a fixed element is of F is contained in E is the so E is, so gamma is the event that X is at least 1. E is a random set where we take each element of U with probability theta. Yeah. So we're interested in, does a fixed subset of U of size L contain, so this is going to be the size of F times theta to the N. Because we have this is the probability that some fixed element is in F, and we just take the use linearity of expectation. And now if we have, say, let me say, suppose that theta is equal to C times F to the minus 1 over L, then here the cardinality of F vanishes and we get C to the L.
The value expectation, I think also the sine of F times with theta to the L times with 1 minus theta.
Right, yeah, you're right. Well, no, wait. I don't. I think that for expectation, that's not true, right? We're just.
So the question is, you want to put 1 minus theta to L?
And beside theta to the L, I think so 1 minus theta sine of U minus L.
No, I think this is okay. But this is a subset, right? So for other
Right.
elements outside of this particular set S.
Yeah, we're not looking at is there exact. Yeah, this is a subset. So when I write in here, I mean the subset. This is not that we have this as a subset. So we only care about whether a particular element is contained in E. We don't care at all about, not induced. This very good point. Yeah, so in particular, if we take C as little o of 1, then this will also be little o of 1. So this shows that if theta here is little o of F to the minus 1 over L, then the probability of gamma is little o of 1. So we have the first. So under the condition that theta is at least that, we have the first condition is met. But this is not always the threshold. In some cases, it may not be. A very trivial example is, let's take the family F to be some element X together with all sets S where S are subsets of U minus X of the proper size. So now for this, the event that U contains some element of F is exactly equal to the indicator function for the event that X is contained in E, together with the indicator function for the event that the size of E is at least L. Now it's very easy to calculate the threshold functions for these events individually. This one is exactly what you would expect. This is F to the minus 1 over L. But what is the probability that you contain? We have to contain this element X with positive probability. The only way that that happens is if the probability theta is positive. So here the only threshold, the threshold functions have to be constant. So 1 is a threshold function, for example. And it's just because, So in general, this F to the minus 1 over L is not always the threshold function. So our first kind of our collection of general tools are sufficient conditions that give when is this kind of trivial lower bound on the threshold function actually the correct threshold function. And we have basically three different propositions that we have there of increasing generality and power, but also increasing complexity. So that when you can use the earlier ones, we prefer to use the earlier ones because it's easier. But then when we can't, we have to use the earlier ones. So the first proposition 1 is for the case that L is bounded. So we're talking about L uniform set families is we're taking the underlying size of the underlying universe to infinity, but if each element in F is of constant size, say, then we get the following condition. And for all sets R in U with the size of R is equal to K, where K is anything between 1 and L minus 1. The number of elements in F that contain R is bounded above by cardinality F to the minus 1 minus K over L. Then F to the minus 1 over L is a threshold function. So here we're looking at subsets of our underlying set and asking how many sets contain this one, and if we have a good upper bound on that for all subsets, then this will work. And so, for example, if you consider the example that I was talking about before, where all the sets contain some fixed element x, then we say, well, how many sets contain the fixed element x? All of them. So we have F on this side, and then F to the 1 minus 1 over L on that side, and then we clearly don't have this inequality satisfied. But when L is not bounded, this is obviously not at all useful. So the other two propositions I'm going to mention depend on the following quantity. Say I sub k is the number of pairs S and T such that the intersection of S and T is equal to K. Yes. So now, if the next one is if there exists a positive constant C such that the sum from k is equal to 1 to L minus 1 of C to the k times cardinality F to the k over L times the cardinality of times the number of these particular pairs, the number of pairs that intersect in k points. If this is bounded above by f squared. So this is kind of the total number of pairs, and then we're taking a weighted sum over all the pairs depending on their intersections. And we have to say, so that if this holds, then again, f to the minus 1 over L is a threshold. This holds for any positive constant c, but it has to hold obviously for all the underlying set families here. There's some f is defined for this infinite family of U, and so this U is the asymptotic parameter. Now this, in some cases, we actually want for some applications, we need a more precise control, not only of where the threshold is, but how concentrated the distribution is at the threshold. For example, for a sharp threshold, but even in some cases, we may need. So obviously, this doesn't give any tighter control. So there's one more version. And here we say, for any pair of constants c and c prime, this needs to not be equal. Actually, these need not be constants. These can also be right. And this is a fixed constant. Here, these are allowed to be parameters of the problem, so they can depend on. You can use a different c and c prime for different underlying sets. And so we have a very similar looking condition. Where here we have C prime on the right, but otherwise the same inequality. But what we get is a stronger conclusion. So the probability of gamma, the probability that your random set E contains some element of F, is at least 1 minus C prime minus C to the L. So in this case, if you can choose C and C prime so that so that this is going to 0, these are not necessarily constant. So you can choose, so the point is that you can choose a sequence of C and C prime that are convergent, for example, to 0. And you may be able to show that this holds there should be some, there should be some, this is a little, when this is a little bit, this must be incomplete, right? Oh yeah, I need to tell you what is, what is theta, because theta is going to be C times F to the minus 1 over L. So here we have a random subset L, E, where we choose each element with that probability, and then the probability that we're containing some element F scale. So let's see how we apply these. Okay. So I'm going to talk about basically two families of problems, kind of incidence, problems for incidences between points and affine subspaces of FQ to the n. So here we're going to, we say that if we have L is an L-rich M flat. So by M, yeah.
This proposition 2, for example, is stronger than proposition 1.
So it's easy to see why. It's not very hard. It does take several lines to prove. The idea is that if you look at one fix one set, say we fix one set of F, and there can be it can intersect at most L choose K other sets of that size. So this is, if you work from that, it's quite several lines, but this is the kind of, and it's actually, we did see, is much harder, but it's also, for constant L, it's possible to go the other way and prove proposition 2 from proposition 1 under the additional constraint that L is constant. But I mean, first of all, the proof is more complicated than the direct proof of proposition 2 using the second moment method. That's what's underlying all of this is Chebyshev's inequality. And the bound on L is necessary for the first one to hold. So there's not, you can't just remove the upper bound on L and hope to have anything that looks like the first proposition. So if you want that condition, then you need to, if you want to use the condition, which is easier to check than the condition for proposition 2, you need that assumption on L. So let's say L is an L-rich M flat with respect to, let's say, E, which is now contained in the finite n-dimensional vector space over FQ. And an M flat here is a translate of an n-dimensional subspace. So affine n-plane, for example. If L intersect E is at least L, lowercase l. So here we have a nice L uniform family, which is the sets of all sets of L points contained in M flats. And so we can hope to apply these propositions. First, we have quite a complete answer in the case that M is equal to 1. I believe I'm looking at the wrong page. Maybe I lost the right page. It's okay.
You have M flat,
M flat. So this is a translate of an n-dimensional subspace, an affine n-dimensional subspace. So I just like the word flat because it's shorter than affine subspace. That's what I'm. And it's, I mean, it is a standard term. So this is for the property that you contain. There's L-rich line with respect to and the conditions are that n plus q, so either n or q can go to infinity. And L is not too large, so it's bounded above by n log q. Then we get the threshold that we would hope for, which is q to the 2n minus 2. This is the number of lines in fq to the n. You can see this because q to the 2n is the number of ways of choosing a pair of q to the n choose 2 is the number of ways of choosing 2 distinct points. And then we have to divide by q choose 2, which is the number of, because we've now overcounted each line every time that we by the number of pairs of points on that line. So this is the number of points. And we have q choose L. This is the number of L subsets of a fixed line. So then we get is the threshold. Just wondering if I actually have my notes for this. No, I don't. But I think anyway that we can prove this under the additional assumption that little l is bounded. So proof, assuming L is equal to O, big O of 1, and that means that we can use, in particular, we can use proposition 1. And we avoid many more complicated calculations that come into this particular round. So we do have another complementary theorem coming up. The answer is that this is the best possible from our proof, but it's not. In general, we do remove it using a separate argument. In fact, we get above this bound, we get a sharp threshold. And I think actually this is a bigger one. So the proof here, we need to check basically over all subsets the underlying space of size k for k ranging between 1 and L minus 1. So let's consider two. The thing is, because we're looking at the lines, there's kind of two different types of sets. There's a single point, you've got all the lines in the space that go through that point. But once you have more than one point, you've already identified a specific line where it has to lie. So let's break into two cases. First, the size of the set is 1. And so how many lines are there through a point? It's q to the n minus 1 lines are incident to a given point. And then on each of these, we get q minus 1 times L minus 1 L subsets that contain that fixed point. And we need for this to be, and this is some, here L is a constant, so what we get is q to the n minus 1 plus, say, n plus L minus 2. And we need for this to be big O of q to the 2n minus 2 plus L times 1 minus 1 over L. And this is true. I mean, basically, if you plug in 1 here, then you get equality in the exponents and plug in 1 for n. What we get is L times 1 minus, so we get L minus 1 on this side, and we get L minus 1 on this side. So it works when n is equal to 1. And then you can just look at the L plus n minus 2 minus 2n minus 2 plus L times 1 minus 1 over L. And just looking at the n terms, you can see that it's increasing with n. So it's true when n is equal to 1, and it's true when n is greater than 1. So this is just true. And I'm running out of time, so let me just say that it's much easier to check it when you check this for point sets larger than size 1. Actually, on the left, you get something that doesn't depend on n at all. It's just how many L subsets contain a given K subset. Well, if the K subset is not collinear, it's 0. If they're collinear, then it's going to be Q minus K choose L minus K. And here we have no, this n is just going to completely disappear, and we get something that's very easy to check.
Can you explain why Q minus 1 choose N minus 1?
We're fixing one point. This is the number of lines that contain that point.
Right.
And now I'm interested in how many collinear L subsets contain that point. So once we fix the line, there's Q minus 1 points left on that line, and so we need L minus 1 additional points, because we already have the first point, which is R.
You have Q minus 1.
So we fix some point, and first we look at all the lines through that point. Now let's choose one of the lines and say, well, how many subsets of size L are there that contain this point? We have Q minus 1 additional points there, and we need L minus 1 because we already have 1 point. It's in all the sets that we're considering contain that given point. So that's one of these.
So you want L be a subset of E? Is that? No.
L is a integer. It's a parameter of the property. Capital L is, yes, a subset of E. No, capital L is a line. So this, right. So when is there an L-rich line with respect to E? This happens exactly when E contains some set of L points. So maybe the terminology is a little confusing because this capital L is completely disappeared in the proof.
So in a sense, more precisely, you may have to compute the cases where you may have more than L elements on that
But here, what we're bounding is the number. So what we're bounding is this set here. So we're bounding the number of sets in F that contain R. And R here is a single point. So we're not, at this point, so when we check this hypothesis, the set E is not there. Right? We're not interested in, all we're doing here is checking this condition. And there's no reference to E, there's no reference to theta, there's no reference to anything like that. Once we check this condition, we know that the set F, the set family F has the right threshold we're looking for, which is this. So we don't need to worry about the sets. Because F only contains sets of size L. F is L uniform. F is the minimal elements of this. So we have some property that's defined by a larger family, the upset of L. But we're only looking at the minimal elements. F is really only the minimal elements of the family.
So in this case, S is the
R is a single.
R is a single point.
S is an element of F. So S is L points that are collinear.
Yes.
And we want to count how many sets of L points that are collinear there are that contain a given single point. And it doesn't matter which point we choose, it's always the same number. So here we're just fixing R to be some single point, and then we check. Okay. So we have this condition. Now, what if this condition on L doesn't hold? So here we have theorem 2. Again, take either L or Q to infinity, and take L is little omega of n log Q. So the complementary part. Then Q over M, or I'm sorry, N over Q to the M is the threshold. As a sharp threshold, even sharp threshold. Now, I don't want to spend too much time talking about this. I will say it uses a completely different argument. This is a Chernoff bound, and also these two thresholds look quite different, but if you plug in L is equal to n log Q here, you'll see that they're within a constant factor of each other. They only are different by like a 1 over e squared factor, basically. And the third observation or comment is that actually we get a very kind of different kind of threshold result here. Not only is it a sharp threshold, but what you see is that when the probability theta moves past this this threshold, below the threshold we have there's no L-rich M flats, and above the threshold, almost all L-rich M flats are in fact, or almost all M flats are L-rich. So to prove the kind of non-trivial part of this, we just forget about the entire finite vector space. We just look at one single M flat and say, on this M flat, all our points are coming independently, uniformly at random. And the expectation, when we cross this threshold, the expectation goes from below 1 to above 1, or the expected number of L sets, L subset. The expected number of points on the, expected number of points on the M flat goes from below L to above L. And in fact, what you see is that it concentrates very strongly at L. So if you have 1 plus epsilon, the expected number of points on each M flat is 1 plus epsilon times L, then actually the probability that any given M flat doesn't contain so many points is negligibly small. So we have a very sharp, the sharp threshold has instead of going from there doesn't exist a L-rich M flat to there does exist an L-rich M flat, we go from there doesn't exist an L-rich M flat to almost all the M flats are actually L-rich. This is, L has to be large.
Any large that we have the same threshold.
I probably must have miswritten it. Yeah, that's a good question.
You can put
I wrote the. Is that better? Yeah, I'm sorry. Good catch. Yes, and that makes it more clear because there's q to the n points on a. Yeah, but now this makes sense. It doesn't depend on n. Right, and it makes sense that it doesn't depend on n because we forgot that we were living in an n-dimensional vector space and only are looking at our m-dimensional space. So actually, there is some complication when we try to apply this approach to a higher dimension for m greater than 1. But basically, if you take, I'm just trying to decide whether, I don't have time to talk about everything I wanted to talk about. I'm just going to skip it actually and talk about the next thing, which is to say that E is an M blocking set. If it intersects all M flats. So in general, M blocking sets are very poorly understood. We don't know how many there are. We don't know how large the minimal ones are. We don't know. We know a lot about them, but very far. Just to give an example, say for n at least 3, the largest minimal one blocking set. So if you want to block the lines, is well, it's at least n to the q to the n minus 1/2, and this is only if q is a square. So q is equal to p for some power of a prime p, then you could get a construction that has n to the minus 1/2 in the exponent. And at most 1 minus 2 to the minus n times q to the n. So we don't have a construction of this size, but we know that there aren't any blocking sets that are larger than 1 minus 2 to the minus n times. And here we have, so n is fixed and q is the asymptotic prime, especially for this construction. So the lower bound comes from Hermitian varieties that were investigated by Bose in the 1960s, and the upper bound is corollary to the work on the Kakeya set conjecture by Beer and many other sets. But between these two, we have no progress. So now we're not, since we're not looking at a pattern, F now is the minimal blocking sets, but we don't know how large they are, then we don't know how many there are. It's not L uniform. But what we can do to approach this is pass to the complement. What do we know about the complement of a blocking set is that it doesn't contain, the complement of a blocking set doesn't contain a M flat. So but here, yeah. N is constant. Yeah, thanks. Right, so if we fix n and take q to infinity, that's the setting that I'm thinking about here. If you fix q, like if you fix q equals to 3 and take n to infinity, now this is the capsule. So there are many very famous questions in finite geometry that can be stated in this form about what is the size of them. How large can a minimal blocking set be, or how small can a blocking set be? Depending on different parameters based on n and q. So, but the key observation that lets us get some probabilistic information, or some information in this setting, is that the complement of a blocking set doesn't contain an M flat. So, but in order to use this information, we're typically going to think about the blocking set as being very small. A typical blocking set is, we don't even know if they exist that are larger than this, and this is a very special algebraic structure. The typical size, a kind of general blocking set, is going to be very, very small. So you need a very sharp concentration. What we need to do is have a very sharp threshold bound for the M flats to translate it into just a standard threshold for blocking sets. So to this end, we have this lemma. So the event is that E contains an M flat. And the setting is that n plus q is going to infinity, and m is at most n over 2. Then we have 1. If theta is so gamma here is the event that E contains an M flat. Unfortunately, I've erased the definitions of the threshold functions that were up here before, but the big difference here is that we've moved so q to the m is L. L is q to the m. It's all the points on an m. And so this is minus 1 over L in the exponent. So instead of having a little o of f to the minus 1 over L, we managed to move the asymptotic notation inside the parentheses. So if you imagine we have some, let's suppose that this function here is like t to the f to the minus 1 over L. This is equal to t to the minus 1 over L times f. So t is just some number that's going to infinity. But now this, if L, t is some function that's going to infinity here. Like I'm just looking at this condition here and seeing how does this compare to the previous condition that we had, which was, this is what it would be in the threshold function, if we just were trying to prove the threshold function. The point is that this could be very, very, very close to 1. It doesn't actually have to go to infinity anymore, because L may go to infinity much faster than t. And that is, in fact, in the application what we get. So can I have another, like, 5 minutes? The time, according to the clock, I'm finished. Okay, clock is going to dismiss. So now the main application of this is the event that E is a blocking set. So here we have that q is going to infinity, m is a constant, and n is not too large. Where q to the m time over log q. And this is kind of critical to the method, unfortunately, because we have this assumption that 2m is less than n. And this assumption comes from the fact that when m is larger than half n, every pair of flats intersect. So you can imagine if we're trying to bound the number of pairs above by, here we have some subset of the pairs, but if this is already f squared, then this is a hopeless condition. So in general, I'd be interested to remove this condition from this theorem, but using our method, you can't do it. Then n over q to the m log q is the threshold. And this is more or less what we would expect. So I'm not going to give a full proof, but we can see one side of it. So let's suppose that theta is little omega, the threshold function there. Then 1 minus theta, well, theta is we're choosing E, so 1 minus theta is the probability that we're choosing elements of E complements. So we're going to apply this lemma down here to the complement and then show that. So this is mos E to the minus theta is E to the minus little omega and Q to the minus m log Q. Pull that log cube out, Q to the minus omega n, Q to the minus m. Now for fixed m, the number of, so if we have f prime is the family of, f prime is the m flats, yes, exactly. The size of this is going to be q to the theta n. Really, it's q to the m times n. This is n times m plus 1 minus m times m plus 1, something like this. But the point is that if m is a constant, then all of this is really linear. If we fix n as a constant, this m as a constant, this is linear in n. So we can pull this n out and get cardinality f to the minus omega q to the minus m. And of course, we could split this up into an omega 1 term and q to the m term and pull the omega 1 term inside, and we get that this is omega f to the minus q to the minus m. And this then is the hypothesis that we need for the first one of this storm. For now. Anyway, this is the number one, condition 1 there. And so what this tells us is that the probability that E complement contains a M flat is little o of 1, and hence the probability that E is a blocking set is 1 minus E1, which is exactly what we wanted to show to get the threshold result from this here. So that's all I have time for today.
Thank you. Any questions?
Can I ask some relevant questions? So far you assume that all the entities are finite, meaning that they are finite dependent. But suppose suppose there is some dependency, but some reform, like their probabilities are maybe exchangeable. So after that, do they have any result about such a setting?
So, I mean, sometimes you can do a kind of coupling argument to move from one setting to the other. Other than that, I don't really know. I think that Deb is the person to really ask more generally about what people do in this area. I will say that I didn't manage to get to it, but when we're considering L flats L-rich M flats where M is larger than 1, this condition here doesn't work immediately. What we have to do is, instead of looking at L-rich M flats, we pass to a subfamily of the L-rich M flats and apply the lemma, this proposition to that family, and then move back. And we do have to kind of then to bound the size of the subfamily, we kind of use an inductive hypothesis. But in this case, for the sort of L+1 rich, but here a different probabilistic setting where instead of considering choosing each point uniformly independently at random, we say, well, we have exactly the expected number of points, and we check it uniformly at random over all such sets. And here, there's very standard machinery to move from the one model to the other. But for other interesting models, I really just don't know what people have done in the area. But there is an expert here. It's just not me.
Talking about these propositions, so are there some standard theorems, maybe on random graphs, where this gives an easy corollary to the existing threshold theorem?
Yeah, I would expect so. I know that proposition 1 has definitely appeared in the literature many times. It's not new. Proposition 2 and 3, I mean, it's not like, I've never seen them written down in this form, but it's not like the underlying. I imagine that you could go to some theorems on random graph where they apply the second Roman method directly and see that, oh, if we don't have to go through all that work, we can just apply this proposition, which is encapsulating exactly the application of the second Roman method. I don't know, to be honest. But proposition 1 is not at all new, and propositions 2 and 3, as far as I know, are new, but I don't think that they're fundamentally advancing the art of the probabilistic in this field.
Any other questions? So let's thank this.